In this collection of videos, I'd like to introduce some of the basic ideas behind regression and error analysis, and in this particular instance, the residual sum of squares error measure. So what I'd like to do in order to introduce regression and what we're doing here is give you a motivational and interesting study. So in 1972, researchers at Stanford created a test that you may have heard of called the marshmallow test. And the idea behind it was this. 5-year-old children were placed in a room with a marshmallow or other kind of desirable treat right in front of them. Now, the researchers began in the room with the children and explained to them that they were going to be leaving the room and that when they returned, if the marshmallow was still around and the child had not given in to temptation and eaten it, then this child would actually receive an additional marshmallow or special treat, so they would have 2 special treats. However, if the child gave in to temptation at some point in time when the researcher was out of the room and ate the marshmallow, then they would not receive this additional treat. Now, the researchers were out of the room for about 15 minutes, but the children did not know that ahead of time. And after this test, children were monitored for a long time. And around 1990, a paper came out showing some amazing correlations with the marshmallow test. Namely, the longer the child waited to eat the marshmallow, in particular if the child was able to wait all the way the whole 15 minutes until the researcher re-entered the room, that was correlated with tremendous outcomes in almost every measurable way. The children who could wait the longest had the lowest BMIs. The children who could wait the longest had the highest SAT scores. The children who could wait the longest generally indicated that they were very happy in life. All sorts of positive measures were correlated with being able to wait a long time before eating the marshmallow. And conversely, the children who immediately gave in and ate the marshmallow had lower SAT scores, overall reported being less happy, had higher BMIs, etc. All the things that they measured in this test, the children who could not wait scored less desirably later in their life. Now, what this led to was this huge frenzy. People were absolutely fascinated by the marshmallow test, and they were writing books about how to increase self-control among children so that they could live these happy lives. And so it was this huge phenomenon that was going on in the 90s, where the underlying idea was, let's imagine that we have all this data from the children that were in the study. They're no longer children now. Remember, they were children in 1972, and this paper was reported in 1990. So we have all of this data about how much time it took before the child ate the marshmallow. So children who gave in right away had, in whatever life outcome you wanted to measure over here on your y-axis, the children who couldn't wait very long scored poorly, and the children who waited a long time scored well. And so the idea was, we have all this data. Is there a way that we can make a predictive model where you give me as input the time it takes for your child to eat the marshmallow, and what the model will do is predict as an output for whatever life event you're interested in measuring, how well your child will score on that event. And parents all over the country were looking at this predictive measure to see how their children would fare later on in life. And this idea of having a bunch of data, seeing a desirable outcome, and trying to come up with a model that can predict the outcome of new data is really the idea behind linear regression. Now, I must point out to you, it's incredibly important that I point out to you that the marshmallow test is a big, fat fraud. So for a long time, the marshmallow test was the word of God, and people were absolutely obsessed with it. However, many studies between the 90s and today failed to reproduce the outcomes that were perceived and measured in the original marshmallow test. And in fact, a really important recent study from 2018 found that really what the marshmallow test was studying was income inequity. You can imagine a child from a well-off home who had a great breakfast before they walked into this room and had to face the temptation of eating a marshmallow would fare a whole lot better than a child who walked in there who knows when they had their last meal and they're starving and they never get that kind of treat. You can imagine that income inequity would play a large factor in how long it takes for a child to eat a marshmallow. And income inequity also has a huge hand in how people tend to do on measures like SAT scores and BMIs and depression. So there really isn't much going on with this marshmallow test other than a big old measure of income inequity. So don't be fooled by the marshmallow test. Self-control and willpower, while desirable traits, are not a magical predictor of happiness in life. Nor should I say is income, but that's a different story. But what I do want to take away from the marshmallow test is the big picture. We have some sort of collection of data. We want to see, from the data we were able to see and observe, if we can come up with some sort of function or model that will take in a new datum or individual data point as an input and predict an output when that data point was previously unseen by what we observed. Can we still make predictions about this new input and what we expect the output to be? That general idea is the idea behind linear regression. There's another idea that we'll be studying, which is the idea of, once we have a model, how do we know how good it is? I have a model here with a line that's drawn basically through what looks like the middle of that data. But what can I do to measure just how accurately that model represents the observations that I'm seeing here? Ideally, I'd like to come up with something that would say a model like the one shown here is a good model, but a model that just blatantly predicts we all have the same life outcomes would be a bad model. That's going to be the idea behind what in the regression case is called the residual sum of squares, but more generally in data science is the idea behind an error measure. What is the error or the difference between what is actually observed and the model that we're using?